This video will introduce the difference between signed and unsigned numbers. Then we will discuss how this concept of signed and unsigned is a misrepresentation of what is really happening inside a computer. Finally, we will gain some hands-on experience working around different limitations and pitfalls of fixed-width binary numbers. Let's begin with a quick review of how binary numbers work. The place values, when we are working with binary numbers, are the ones place, the twos place, the fours place, the eights place, etc. If we have this particular bit pattern right here, then we can see that we have a 1 in the 128th place, a 1 in the 32nd place, a 1 in the 8th place, and a 1 in the 4th place. When we add the value of our place values together, we get a total of 172. If we want to represent the smallest possible binary value, we could just put zeros in each of the bits, and that would give us a value of 0. If we wanted to represent the largest possible 8-bit binary value, then we can put a 1 in each of our bits, and that would give us a total of 255. Here we have a table which shows all of the possible bit patterns for 8-bit binary numbers. We can see that our smallest value is 0, and our largest value is 255. A major limitation of this system, however, is that we have no way of representing negative numbers. Now we're going to look at a different system for representing binary values. In this system, the last 7 bits still represent the same place values that they represented before. The only difference is that our leftmost place is going to represent negative 128. So if we have the same bit pattern that we had before, then we can see that that will give us negative 128 plus 32 plus 8 plus 4 for a total value of negative 84. The smallest possible number that we could represent using the system can be achieved by putting a 1 in the negative 128th place and a 0 in all the other places. This gives us a total of negative 128. The highest possible number that we could represent can be achieved with a 0 in the negative 128th place and a 1 in the rest of the places, therefore giving us a total of 127. If we look at the chart of all the possible bit patterns, we can see that the 1s over here in the negative 128th place cause the numbers that are in the bottom half of the chart to become negative. So this allows us to represent values ranging from negative 128 all the way up to 127. These two systems are the most common systems for representing binary values in computers. The first system we call unsigned numbers. Only numbers which are not negative can be represented. The second system we call signed numbers, which allows us to represent both positive and negative numbers. The disadvantage of signed numbers is that we only have half the range in the positive direction that we had with unsigned numbers. So with unsigned numbers, we were able to go all the way up to 255, but with the signed numbers, we could only go up to 127. Another name for the particular system of signed numbers that we used is called 2's complement, so you may see that name around. Our system for representing signed binary values can work for any bit width. In the case of 12 bits, we have the following place values. So in this example, our bit pattern gives us a total value of negative 220. The place values for an n-bit signed number will always have this form, where the leftmost bit represents the negative of what it otherwise would. When people speak about signed and unsigned numbers, they do so in a way which implies that signed and unsigned numbers are a real thing, but this is not the case. The only thing that really exists is bit patterns. And bit patterns are just a sequence of zeros and ones that are stored inside of your computer. It is not until we interpret that bit pattern that we get something that has a meaning. We could choose to use the unsigned interpretation of this bit pattern, which would give us the number 172, or we could choose to use the signed interpretation, which would give us negative 84. So strictly speaking, there is no such thing as a signed number or unsigned number. There is only the unsigned interpretation of a bit pattern and the signed interpretation of a bit pattern. However, since it is a little bit of a mouthful to say signed or unsigned interpretation of a bit pattern, when we describe a variable or register as containing a signed or unsigned value, what we're really saying is that what we really care about is the unsigned or signed interpretation of the bit pattern inside of that variable or register. Now that we are familiar with signed and unsigned numbers, we can explore how this impacts programming in assembly. Here we have a simple program that just adds 5 to T0. If we take a look at the machine code for the add immediate instruction, we can see that there's 12 bits that are being used to represent the immediate value. The immediate value is currently 5 because we have a 1 in the ones place and a 1 in the fours place. This 12-bit value is a signed 12-bit binary number. And so you'll notice that if we flip the 1 bit at the beginning, this value turns negative because the bit on the far left is the negative 2048's place, just like we saw in the example earlier. In the last video, we learned that the add immediate instruction is often used to store particular values into a register. But what if that value that we want to store is too large for the add immediate instruction to handle? In this case, 5000 is outside of the range from negative 2048 to positive 2047, which is what a 12-bit signed value can hold, because that's all that we have space for inside of the add immediate instruction. In order to work around this issue, we need to introduce a new instruction. The new instruction is called load upper immediate. If we run this program, we can see that right now we're getting 4096 as the result when we load a 1. To understand what's going on here, let's take a look at the machine encoding of this instruction. Here we can see that we have a 12-bit immediate value that's being used to encode our immediate, which is currently just this 1 value right here. The load upper immediate instruction works by taking whatever these 20 bits are, and it copies them directly into the leftmost 20 bits of the register that's named by the instruction. If we come over here to our register view, we're going to switch the mode to binary mode, and we can see now the exact bits that are inside of all of our registers. When we do the load upper immediate instruction here, we can see that we have a 1 right here, and the rest of these are all zeros, because inside of our instruction here, the immediate value contained a bunch of zeros and a 1 right here. And since these 20 bits are located in the higher place values, this instruction makes it possible for us to load larger values into a particular register. However, it always sets these 12 bits to 0. If we switch back to the signed interpretation, we can see that by putting a 1 here, we're able to load 4096 into the T0 register. If our goal, though, is to load 5000, we can use a load upper immediate instruction with an add immediate instruction to get our desired results. So if we change this now to 904 and run our program again, we can see that first, if we run this program step by step, after the load upper immediate instruction executes, we're going to load the 4096 into this register by copying those 20 bits directly over. Then, when we step forward again and do the add immediate instruction, it's going to add 904 to that result and give us 5000 as the final value that we have inside of T0 in this case. Now it's kind of cumbersome when you want a particular large value to be loaded into a register to have to figure out what value you need here and here to get this instruction pair to give you what you're looking for. So when we use the load immediate pseudo instruction, we can just put larger values directly into it. When we build the program, the assembler will automatically translate this load immediate pseudo instruction into 2 real instructions, the load upper immediate and the add immediate, and it will figure out exactly what constants it needs to put in here in order to give you the desired result that you're looking for. So if we run this program now, we can see that we're loading 5000 into both of our registers. If you would like to solidify your understanding of the concepts in this video, you can go to my website, visualemulator.com, open the course catalog, go to Assembly Basics, and complete Unit 2, signed and unsigned numbers. See you in the next video.